Modern industrial construction integrates cutting-edge machinery and technologies, revolutionizing efficiency, safety, and scale across large-scale building projects. The intricate process of connecting drill pipes on a drilling rig in Canada, showcasing the combination of precision, strength, and teamwork required in the oil and gas industry. The operation begins with workers positioning individual drill pipe sections near the rig floor, preparing them for assembly. Each pipe is carefully inspected for structural integrity, ensuring there are no cracks or defects that could compromise the drilling process. Once ready, the pipes are lifted and aligned vertically using heavy-duty hoisting equipment, while workers maintain close communication to coordinate movements and prevent accidents. The actual connection process is meticulous. Workers use specialized wrenches and torque tools to thread each pipe segment securely into the one below it. This threading must be precise to prevent leaks and ensure the pipes can withstand extreme pressures during drilling. Safety is paramount. Each connection is double-checked, and protective gear is worn at all times. The rig floor becomes a controlled environment where every movement is deliberate, reflecting years of training and experience. To assist with the heavy weight and alignment, chains and guidelines are often employed. These help stabilize the pipes during lifting and threading, minimizing strain on the crew and reducing the risk of mishaps. In larger rigs, hydraulic or motorized tongs may replace manual tools, allowing faster connections while maintaining precision. Despite technological assistance, much of the process relies on human skill, as workers must judge angles, torque, and alignment in real time. Once a pipe section is securely connected, the assembly is gradually lowered into the wellbore. This step is repeated continuously, adding pipe after pipe until the desired depth is reached. Throughout the process, constant monitoring ensures that the drilling string remains vertical and aligned. Any deviation could damage the drill bit or the well itself, highlighting the critical nature of these connections. The video emphasizes not only the technical challenges but also the teamwork and coordination required on a drilling rig. Each worker plays a vital role, from lifting and guiding pipes to tightening connections and monitoring safety protocols. The rhythm of the operation reflects a combination of human endurance, mechanical precision, and careful planning. By the end of the sequence, viewers gain a clear understanding of how drill pipes are systematically connected to form a reliable and robust drilling assembly capable of reaching deep underground resources safely and efficiently. The resurfacing of a highway such as Interstate 57 begins with thorough preparation of the existing pavement. Once crews have milled down the old surface and cleaned the base, the first visible step in concrete resurfacing is the installation of supporting hardware commonly known as chairs and reinforcement bars, rebar. Workers carefully lay plastic or metal chairs at regular intervals across the width of each lane in order to elevate the rebar grid to the correct height above the base, ensuring the fresh concrete slab will have adequate reinforcement throughout its thickness. With the chairs in place, steel rebar arranged in a pre-designed mesh pattern is laid across all chairs, forming a sturdy structural cage. At intersections or joints, rebar may be overlapped or tied with wire to maintain continuity and strengthen potential stress points. Once the reinforcement is properly supported and double-checked, the next critical phase is concrete placement. A concrete mixer truck arrives at the worksite, and a chute or pump system is positioned to deliver fresh concrete directly onto the prepared lane. As the concrete flows out, a crew of laborers begins to spread and distribute the material evenly across the lane's width. It is essential that the concrete is placed uniformly to avoid voids or weak spots. As soon as sufficient volume accumulates, a mechanical screed, often a vibrating board, is used to level the surface roughly, striking off excess concrete and creating a nearly flat slab at the target elevation. But coarse leveling alone does not guarantee a smooth, durable driving surface, so the finishing stage follows. After screeding, hand finishing crews move in to carry out more delicate work. Using long, straight edges are bull floats. They gently move across the lane's surface to smooth out ridges and fill low spots. This ensures an even, planar surface before initial set. Next, they employ edging tools along the lane, boundaries, and joints to compact the concrete edges and reduce the risk of chipping or cracking. Soon after, as the concrete begins to stiffen, a power trowel may be used over the slab to further compress and smooth the surface, producing a dense, hard-wearing finish. For some lanes or sections, particularly narrower shoulders or ramps, the finishing may be done entirely by hand, using hand trowels and floats, to allow greater control and precision in tight or complex areas. As each lane is finished, workers mark expansion and contraction joints at predetermined intervals. These joints are typically saw-cut or manually grooved to control cracking and allow for thermal expansion. After joint finishing, crews clean off any excess concrete around the edges and apply curing compound or cover the slab with plastic sheeting to prevent rapid moisture loss. Curing is critical. Maintaining a moist environment for several days allows the concrete to reach its designed strength and prevents surface shrinkage or cracking. Finally, once the concrete has sufficiently cured, often after several days, the lane striping can be applied, traffic barriers repositioned, and the newly resurfaced section opened to traffic. Over its lifetime, this renewed concrete slab will provide improved ride quality and a smooth, durable surface for vehicles traveling along I-57. In summary, concrete resurfacing on a major highway involves a carefully choreographed sequence. First laying down support chairs and rebar, then pouring and spreading concrete, followed by mechanical screeding, and finally detailed hand finishing of each lane. Proper jointing and curing finish the job, ensuring a road surface capable of bearing heavy traffic with longevity and reliability. The CMIE3 Rapstar series is a state-of-the-art counterflow asphalt plant. Aggregates pass through an optimized drying and heating system with sawtooth flights, ensuring energy-efficient processing. Cold and recycled materials enter the outer chamber, combining with hot virgin aggregates for precise temperature control up to 371 degrees Celsius. Advanced radiant and conductive heat transfer maximizes efficiency while reducing burner output. Materials are then mixed with asphalt, fibers, and fillers in a fully integrated zone, achieving low emissions, high recycling, minimal maintenance, and industry-leading cost-effectiveness per ton. Dragflow's slurry pumps and dredging systems are engineered to handle the world's most demanding sediment removal tasks, offering a combination of high efficiency, hydraulic power, and exceptional durability. At the heart of this technology is the high-chrome agitator, a robust component designed to break up compacted solids and maintain continuous material suspension around the pump intake. Manufactured from high-chromium wear-resistant alloy, the agitator withstands abrasive environments where sand, gravel, silt, clay, and mineral residues rapidly erode conventional components. By constantly creating a powerful vortex, it enables the pump to move dense slurries with minimal clogging and significantly increase throughput. Complementing the agitator is Dragflow's innovative jet ring system, which uses high-pressure water jets to enhance the disaggregation of sediments. This system is particularly useful when dealing with cohesive materials such as clay, compact mud, or fine silts that tend to form stubborn layers on the seabed or in settling ponds. As pressurized water is directed in a controlled pattern around the suction zone, the jet ring system liquefies and loosens the material, reducing the load on the pump and allowing higher efficiency. This feature is essential for operations where precision sediment removal and continuous flow stability are required. For environments containing consolidated or rocky layers, Dragflow integrates two lateral excavators, which provide additional mechanical cutting action. These hydraulic excavators rotate on both sides of the pump, shredding and fragmenting hard deposits that water jets and agitators alone cannot dislodge. The combination of agitator, jet ring, and excavators gives the system exceptional versatility, allowing it to process a wide range of materials from soft sludge to compacted sand, limestone deposits, and industrial waste. This modular approach ensures operators can adapt the pump to specific site conditions quickly and effectively. Dragflow equipment can be mounted directly onto heavy machinery, most commonly through a hydraulic dredging unit connected to an excavator boom. This configuration transforms a standard excavator into a powerful mobile dredger capable of working in confined areas, near shorelines, or in remote sites where traditional dredges cannot be deployed. The hydraulic power supplied by the excavator ensures consistent torque and pumping performance, while the extended reach of the boom allows sediment extraction at considerable depths. For more concentrated cutting capability, Dragflow offers the hydraulic mono cutter head, an attachment designed to provide focused cutting force for extremely consolidated materials. This single high-torque cutter breaks solid deposits into pumpable fragments, making it ideal for mining tailings, hard riverbeds, and dredging tasks involving sediment layers mixed with debris. In addition to pump attachments, Dragflow supplies complete hydraulic and electric dredges, built as integrated systems for large-scale dredging of lakes, rivers, harbors, and industrial basins. These dredges can be configured with floating pontoons, winch systems, and automation features tailored to each application. They are designed for long operating cycles, energy efficiency, and ease of maintenance. Modern operations benefit further from Dragflow wireless remote-controlled dredges, which allow operators to manage dredging activities from a safe distance. Using remote control improves safety in hazardous environments such as contaminated lagoons or unstable tailing ponds, while also enabling precise maneuverability and automatic depth control. For maximum mobility, Dragflow has developed the amphibious multi-purpose dredge, a machine capable of operating on land, in shallow water, and in full aquatic environments. Its self-propelled, tracked undercarriage allows it to move across marshes, swamps, or soft terrains where traditional dredges cannot function. The main applications for Dragflow systems include river and harbor dredging, mining tailings removal, industrial sediment cleaning, pond desilting, beach reclamation, dam maintenance, and environmental remediation. Their equipment is used wherever powerful, reliable slurry pumping is essential for restoring water flow, maintaining infrastructure, or recovering valuable materials. The chip and seal process begins with a distributor truck applying a uniform layer of hot liquid asphalt onto the prepared roadway. After the first pass, the crew checks the coverage and makes additional passes to ensure a consistent coat. Next, the chip spreader is hooked onto a supply truck, which provides clean aggregate often. Number 8 stone, commonly used for this type of surface. As the truck moves forward, the spreader opens its gates and evenly broadcasts the chips onto the fresh asphalt. A water truck follows to control dust and support compaction. The embedded stone creates a durable, skid-resistant surface at a significantly lower cost than traditional asphalt paving. Typically, 2 or 3 coats are applied to enhance strength and longevity, allowing counties to complete many miles of roadway each season. The KeystraK K5 mobile screener is a high-performance track-mounted screening unit engineered for demanding applications such as topsoil, compost, construction debris, and recycled aggregates. At the core of its design is a large double-deck screen box, measuring approximately 4.9 meters times 1.5 meters, providing more than 14 square meters of effective screening surface. This allows the machine to process feed sizes up to 800 millimeters and achieve impressive production rates of up to 500 tons per hour, depending on material and configuration. The K5 supports a wide range of screening tasks, from pre-screening and scalping to fine separation, and can be configured for 2-way or 3-way splits. For particularly challenging or sticky materials, it can be equipped with the optional Bivitech flip-flow screen box, ensuring consistent throughput under difficult conditions. Designed with operator convenience in mind, the K5 incorporates remote-controlled operation, clear service access points, and simplified maintenance features. Its efficient Cat C4 or Deutz engine, combined with load-sensing hydraulics, significantly reduces fuel consumption while maintaining strong hydraulic power. Despite its high capacity, the KeystraK K5 remains compact and fully mobile, with the ability to track during operation. This makes it an excellent solution for contractors requiring both performance and flexibility on the job site. The time-lapse shows the overnight installation of bridge beams for the new Gordon Avenue interchange on US 89. Despite snow, rain, and sleet, crews worked continuously to place the massive precast members Each beam weighs around 60,000 pounds, and more than 500,000 pounds of concrete were set in a single shift. Large cranes carefully lifted and positioned the beams onto the prepared supports, while ground crews guided alignment under bright work lights. Step by step, the structure took shape, demonstrating precise coordination, heavy lifting capability, and the determination to keep the project moving forward through harsh weather. The construction of the new Echo Bridge on I-84 was carried out using accelerated bridge technology combined with a geosynthetic reinforced soil foundation to minimize both time and cost. The process began with the demolition of the existing structure, where crews systematically removed the old deck and supporting elements. Once the site was cleared, excavation teams prepared the abutment zones and installed successive layers of compacted granular fill. Between each layer, geosynthetic reinforcement was placed to create a stable GRS foundation capable of supporting the new bridge loads. After the reinforced soil structure reached its designed height, crews installed precast concrete elements to form the abutments and wing walls. This modular approach allowed most components to be delivered and placed rapidly, avoiding lengthy on-site formwork and curing times. Next, large cranes lifted the precast bridge beams into position, aligning them precisely across the newly constructed supports. Workers then secured the beams, installed diaphragms, and prepared the deck surface. Once the deck reinforcement was set, concrete was poured and finished to create a smooth, continuous driving surface. Guardrails, approach slabs, and final grading followed, ensuring a seamless transition between the bridge and the roadway. Thanks to the use of accelerated bridge construction and GRS technology, the entire replacement process was completed far faster than traditional methods, significantly reducing traffic disruption and project expenses. The renewal project on the Chugoku Expressway between Suita Junction and Kobe Junction focused on completely replacing the northbound Mitsuji Bridge, which had been in continuous service for more than 50 years. As the structure had reached a state of significant aging, a full overhaul was required to improve safety, restore long-term durability, and secure the reliability of this critical expressway corridor. The project began with the dismantling of components on the existing superstructure. Crews first cut and removed the wall parapets and the deteriorated concrete deck slab. This phase required precise cutting operations and controlled demolition, ensuring that debris did not fall onto the roadway below. Once these upper structural elements were cleared, workers proceeded to remove the aging steel girders. Because the bridge spans directly over National Route 423, Shin-Midosiji, ensuring the safety of drivers was a central priority. To manage this safely, traffic on the underlying roadway was rerouted through temporary lanes. These traffic shifts were carefully coordinated and carried out only during late-night hours, when overall traffic volume significantly decreased. The same nighttime approach was later used during girder erection to further reduce risks and minimize inconvenience. While dismantling works progressed, crews simultaneously assembled the new steel deckplate girders on the main line of the Chugoku Expressway. This ground-level assembly was one of the key strategies that contributed to shortening the overall construction schedule. By prefabricating and welding the deckplates and girders in a controlled environment, installation time during road closures could be greatly reduced. The replacement superstructure uses a high-durability steel orthotropic deck, a modern design known for its strength, reduced weight, and extended service life. To address the risk of fatigue cracking, a common challenge in welded steel decks, engineers adopted an all-around welded structure at the intersections of longitudinal flat ribs and transverse ribs. This full-perimeter weld system was developed specifically for projects involving the replacement of old concrete decks with steel orthotropic decks. It ensures greater resistance to repeated heavy traffic loads and significantly prolongs the fatigue life of the bridge. Once the new girders were lifted and set in place, crews connected the deck plates using countersunk high-strength bolts. These bolts help reduce surface protrusions, which is important for maintaining uniform waterproofing quality and achieving smoother, more durable pavement. This design also improves work efficiency during future pavement maintenance or resurfacing operations. Following girder installation, the construction team applied waterproofing to the concrete deck surface, replaced the expansion joints, and completed necessary pavement repairs. Another technical highlight of the project was the adoption of precast wall parapets for the first time on a steel orthotropic deck in this region. These parapets were anchored to the steel deck using anchor bolts, and each block was later connected using pre-stressed steel tendons. Before full-scale implementation, impact load tests were conducted with life-size specimens to ensure that the anchorage system met all structural performance standards. After parapet installation, the steel deck surface underwent thorough cleaning, and paving operations followed. The surface layer used FFP full-function pavement, which provides effective anti-icing performance and improves winter driving safety. Once paving was complete, final road markings were applied. Through continuous day and night operations over a 16-day period, the bridge replacement was completed exactly as planned, restoring the structural integrity of the expressway while delivering enhanced durability and performance for decades to come. The construction project on State Route 520 near Medina is a major infrastructure improvement aimed at enhancing safety and traffic flow. It includes widening lanes, upgrading interchanges, and improving connections to local roads. Additionally, the project strengthens bridges and adds modern safety features, ensuring long-term durability. This development plays a key role in supporting regional mobility and community growth. Heavy crawler cranes are essential lifting machines designed for the most demanding construction and industrial applications. Mounted on robust steel tracks, they offer exceptional stability and mobility on uneven or soft ground, making them ideal for large-scale infrastructure projects. These cranes are widely used in heavy lifting operations, such as assembling refinery modules, erecting wind turbines, positioning precast bridge segments, and installing large steel structures. Their ability to handle extreme loads with long boom configurations allows contractors to lift components weighing hundreds of tons with precision. In construction sites, crawler cranes play a crucial role in accelerating project schedules. They can be transported in modular sections, assembled directly on site, and configured with various boom setups depending on project requirements. Once operational, the cranes provide continuous 360-degree lifting capability, enabling efficient handling of oversized materials without the need for ground relocation. Their powerful winches, advanced control systems, and wide outrigger-free stance ensure safe performance even under challenging conditions. Beyond infrastructure, crawler cranes are also used in mining, petrochemical plants, offshore yards, and heavy equipment maintenance. Their reliability, versatility, and high lifting capacity make them indispensable machines for modern heavy lift operations, supporting both construction productivity and operational safety.